The story of life on Earth begins long before the complex plants and animals that we recognize today. The early history of life is a fascinating journey that takes us back to a time when Earth was a much different place, its surface still cooling, its atmosphere devoid of oxygen, and the oceans teeming with the beginnings of life. Around 3.8 billion years ago, the first life forms began to appear, although these early organisms were vastly different from anything we see today. They were simple, microscopic, and made up of just a few basic components. But these organisms would be the foundation of everything that followed, laying the groundwork for the extraordinary biodiversity we know today. To understand the origin of life, it's crucial to first appreciate the conditions on early Earth. Around 3.8 billion years ago, the planet was still in its infancy. A world of volcanic activity, constant tectonic shifts, and oceans filled with chemicals that would provide the necessary building blocks for life. Earth's atmosphere, unlike today's oxygen-rich one, was composed mostly of carbon dioxide, nitrogen, methane, and ammonia, with little to no free oxygen. It was a toxic, hostile environment for most modern life forms, but it created the ideal conditions for the first primitive forms of life. The early oceans were rich in organic compounds: carbon, hydrogen, nitrogen, and oxygen. These elements, when combined under the right conditions, could form amino acids, the basic building blocks of proteins. Scientists believe that in the right combination, these molecules could have spontaneously formed the first simple life forms. The warmth of the planet, with geothermal vents in the oceans releasing heat and minerals, provided an energy source, while the mineral-rich waters acted as the perfect medium for life to take hold. One popular theory about the origin of life is the primordial soup theory, which suggests that life began in the oceans as simple organic molecules slowly formed more complex compounds. According to this theory, lightning strikes, volcanic activity, and ultraviolet radiation from the sun may have provided the energy needed to trigger chemical reactions that created these molecules. In 1953, Stanley Miller and Harold Urey conducted an experiment that simulated early Earth conditions and demonstrated how simple molecules, like amino acids, could be created from inorganic compounds using electrical sparks to mimic lightning. This discovery lent significant support to the primordial soup theory. Another theory suggests that life could have originated in the hydrothermal vents found deep on the ocean floor. These vents, often referred to as black smokers, release hot, mineral-rich water into the surrounding sea, creating an environment where organic molecules could have been synthesized. Some researchers believe that life may have begun in these vents, where the conditions were perfect for the first chemical reactions that led to life. The first life forms were incredibly simple, microscopic single-celled organisms that did not resemble anything we would recognize today. These early life forms were likely protocells, basic structures that were the precursors to true living cells. A protocell is essentially a membrane-bound collection of molecules that exhibits some characteristics of life, such as the ability to replicate and maintain an internal environment distinct from the outside. These early protocells could have been made of lipid molecules, fatty acids that naturally form spherical structures in water, known as lipid bilayers. These lipid bilayers would have provided a protective environment for chemical reactions to occur inside, essentially creating the first cell-like structures. Around 3.8 billion years ago, protocells gradually began to evolve into more complex forms of life. The first true living organisms were likely single-celled prokaryotes, organisms that lacked a nucleus. Prokaryotes were the earliest known form of life, and they laid the foundation for all living organisms that would follow, including plants, animals, fungi, and even the more complex single-celled eukaryotes. By 3.5 to 3.8 billion years ago, the earliest true life forms, prokaryotic cells, had begun to appear. These tiny cells, which were no more than a few micrometers in size, lacked a nucleus and were simpler than the cells of modern organisms. The two primary groups of prokaryotes are bacteria and archaea, both of which still exist today and are among the oldest known forms of life on Earth. Bacteria are the most familiar type of prokaryote. They are single-celled organisms that come in various shapes, such as spherical, cocci, rod-shaped, bacilli, and spiral, spirilla. Despite their simplicity, bacteria can perform many of the functions that are necessary for life, such as replication, metabolism, and response to environmental stimuli. Early bacteria would have been the first organisms to harness the energy available in their environment, particularly from chemical reactions involving sulfur, iron, and other minerals in the oceans. Archaea are another group of prokaryotes that are genetically distinct from bacteria. Archaea are often found in extreme environments, such as hot springs, deep-sea hydrothermal vents, and salt flats. Some species of archaea are extremophiles, capable of surviving in harsh conditions like extreme heat, acidity, or salinity. It is thought that archaea may have been among the first organisms to appear on Earth, as they are better suited to the harsh, early Earth environment. In fact, it is possible that archaea and bacteria split from a common ancestor around 3.8 billion years ago. These early prokaryotes were likely chemoautotrophs, organisms that derived their energy not from sunlight, as plants do today, but from chemical reactions with inorganic substances. Some of the first prokaryotes may have used hydrogen sulfide or methane to produce energy, which is a process still used by certain bacteria and archaea today in environments like deep-sea vents or underground ecosystems. Among the most significant early life forms were cyanobacteria, a type of bacteria capable of photosynthesis. Cyanobacteria played a pivotal role in transforming the Earth's atmosphere and making it conducive to the life forms we know today. Around 3.5 billion years ago, cyanobacteria began producing oxygen as a byproduct of their photosynthesis. This early photosynthesis was an incredibly important development because it led to the gradual accumulation of oxygen in the atmosphere, setting the stage for the rise of more complex life forms. Over time, this process created what is known as the Great Oxygenation Event, which occurred around 2.4 billion years ago. The buildup of oxygen in the atmosphere had profound effects on Earth's geology, climate, and biology, and paved the way for the evolution of eukaryotic cells, which are more complex than prokaryotic cells. However, the early Earth was still a very harsh place, and the atmosphere was not yet rich in oxygen. It wasn't until billions of years later, during the Great Oxygenation Event, that Earth's atmosphere would truly change, allowing for the evolution of oxygen-dependent life forms. Though this episode is focused on the first life forms, it's worth noting that by around 2 billion years ago, life had become more complex. The earliest eukaryotes, cells with a nucleus and membrane-bound organelles, began to evolve. This marked a crucial step in the path to more complex organisms, including the plants, fungi, and animals that would come millions of years later. While the first life forms were simple, microscopic, single-celled organisms, they set in motion a chain of events that would eventually lead to the vast complexity of life on Earth. From these humble beginnings, Earth's first life forms laid the foundation for the vast biodiversity that would emerge in the future. The first life forms that appeared on Earth around 3.8 billion years ago were nothing like the complex organisms we see today, but they were the essential building blocks for everything that followed. From simple protocells to the rise of prokaryotes like bacteria and archaea, these tiny microscopic organisms were the pioneers of life, thriving in the hostile conditions of early Earth. While life on Earth began as simple and microscopic, its evolution over billions of years would lead to the explosion of diversity we see today. In the next chapter of our journey through Earth's history, we will explore the rise of eukaryotic cells, the development of multicellular life, and the beginning of the incredible biological complexity that defines our world. This is just one part of the rich tapestry that makes up the story of life on Earth, a tale that continues to unfold today. The first life forms were the pioneers, the forerunners, the foundation upon which the rest of life was built. Without them, the Earth would remain a barren, lifeless rock, one of countless planets in the universe. But with them, Earth became the cradle of life. And that's another step in our journey through history. We've only scratched the surface, and there's so much more to uncover. If you enjoyed this dive into the past, make sure to like, subscribe, and hit the notification bell so you don't miss the next chapter. I'd love to hear your thoughts. What surprised you most? What era are you most excited to explore? Drop a comment below and let's keep the conversation going. Until next time, stay curious and keep exploring the past.